Hello everyone, welcome to the video lecture of this course finite element method. So this is the second lecture of the third module, that is two-dimensional problems, and there we will discuss mainly the scalar variable problems. So in the earlier lecture we have discussed the concept of these two-dimensional problems, then the finite element modeling based on the discretization and the numbering of nodes. After that, we have discussed the concept of the CST and LST elements, that is constant strain triangular element and linear strain triangular element, and the comparison in between these two different elements we have discussed in details. Next, we have seen 12 different formula which we have discussed in this earlier lecture, and based on this total 12 formula we will solve different numericals today. In the earlier lecture we have discussed one numerical only, so today we will be discussing 4 different numericals based on those formula that we have discussed in the earlier lecture. Okay, so let us start this lecture. So the first numerical which is given here, it states that the nodal coordinates of the triangular element shown in the diagram. In figure 1 you can see a triangular element and its 3 different nodes we can see, and their coordinates are also given. Now at the interior point P, the x coordinate is 3.5 and n1 is 0.4, and we need to calculate n2, n3 and the y coordinate at point P. So what is given here, that we are having a triangular element. Suppose the nodes we have denoted as 1, 2 and 3. Now the coordinate for this one, it is 1 and 2, so x1 is 1, y1 is 2. Then in the similar manner, corresponding to coordinate node 2, the coordinate x2 it is 4, y2 it is 3. Then corresponding to this node 3, x3 is 6 and y3 is 4. So these are the three things given. Now inside this triangular element, one point P is given, for which the x coordinate is given 3.5. We need to find the y coordinate of that point P, and the value of n1, this is given here only, it is 0.4. So we need to find the value of n2 and n3, that is the other shape functions. So this is the numerical given here. Actually we need to find the shape functions n2 and n3 and the y coordinate of the point P which is inside this triangular element. So how to proceed here in this numerical? The formula which we will use here, that have been discussed in the earlier lecture. So there we have seen one relation in between the three different shape functions, so that which is that n1 plus n2 plus n3, this is equals to 1. So in this relation the value of n1 is actually given, which is 0.4. So that means n2 plus n3, this is equals to 1 minus 0.4, which is 0.6. Next, to find the coordinate x, there is one relation which is n1 x1 plus n2 x2 plus n3 x3. So if we use this formula, then the value of x is given in the numerical, which is 3.5. Then the value of n1 and x1 it is given. Then the value of x2 and x3, these are also given. So that means we will find one equation in the form of n2 and n3, which we are seeing in equation number 2. So which is 4 and 2 plus 6 and 3. This is equals to 3.1. Now, in equation 1 we have seen n2 plus n3, this is 0.6, and equation 2 we have seen 4 and 2 plus 6 and 3, this is 3.1. So from these two different equations 1 and 2, we are having two different variables which are n2 and n3. So from these two different equations we can easily find the value of n3, which we are getting as 0.35. Now if we put the value of n3 in either equation 1 or 2, then we can easily find the value of n2, which we are getting as 0.25. So this is the procedure by which we have found the value of the shape functions n2 and n3. Now we need to find the y coordinate of the point P. For that we need to use this formula, which is n1 y1 plus n2 y2 plus n3 y3. Now here the y1, y2 and y3, these are the y coordinates of the three different nodes or the corner points of the triangular element. So these are given in the numerical. Value of n1 was given in the numerical, and the value of n2 and n3 we have calculated just now. So we can put all the values in the coordinate equation of y, and we can easily calculate the value of y, which we are getting as 2.95. So this is the procedure by which we have calculated the value of the shape functions n2 and n3 and the coordinate y. So what we have done here, we have used the relation in between the three shape functions, which are n1 plus n2 plus n3, this is equals to 1. After that we have used the formula to calculate the coordinate x, and based from that we have found one equation in terms of n2 and n3. So from the equation number 1 and 2 we have calculated the value of n2 and n3, and that from those values we have calculated the value of coordinate y for the point P, which is inside the triangular element. Okay, so let us discuss the next numerical. So here we need to determine the x and y coordinates of the point P for the triangular element, which is shown in the figure 1. The shape functions n1 and n2, these are 0.2 and 0.3 respectively. So what is given here in this numerical, a triangular element is given which is having three nodes in its corner points, and their coordinates are given. So that means x1, y1, x2, y2, x3, y3, these are given. Now inside this triangular element there is one point P. So we need to determine the x and y coordinates of this point P, and also we need to find the shape functions. It is n3, because the shape function n1 and n2, these are actually given in this numerical. So let us draw the diagram in the required way, where we will draw the point P inside this triangular element, and the coordinate of this point P, it is x and y. So here as the coordinate of the nodes 1, 2 and 3, these are given, so you can easily write the value of x1, y1, x2, y2 and x3 and y3. Now first we need to find the value of the shape function n3, as the values of the shape function n1 and n2, these are given as 0.2 and 0.3. So we can use the relation in between the three different shape functions, that is n1 plus n2 plus n3, this is equals to 1. Now if we put the value of n1 and n2 here, then we can write that n3 this is equals to 0.5, which is 1 minus 0.2 minus 0.3. So the value of n3 we are getting here is 0.5. Okay, so next we need to find the coordinate of the point P. So this coordinate P is inside this triangular element which you can see here, and its coordinate we have denoted as x and y. Now to find the coordinate of this point P, we need to use this equation for x, which is n1 x1 plus n2 x2 plus n3 x3, where n1 n2 n3 these are the values of the shape functions, and x1 x2 and x3 these are the x coordinates of the node or the nodal points or the corner points of this triangle. So here you can see that x1 is 1, x2 is 4, and x3 is 3. So we can put all the values of the n1, n2, n3, and x1, x2, and x3 in this equation of x, and after calculation we will get the value of x is 2.9. So that means the x coordinate of the point P, it is coming as 2.9. Next we need to calculate the y coordinate of this point P. So in the similar manner we can write the equation for the y coordinate for the point P, which is y equals to n1 y1 plus n2 y2 plus n3 y3. Now here all these values for these parameters like n1, n2, n3, then y1, y2, y3 are known to us. So you can put all the values in this equation of the y coordinate, then we can calculate the value of y as 3.8. So this is the procedure with the help of which we have calculated the x and y coordinates of this point P, which is inside the triangle or triangular element. First we have found the value of the shape function n3 as the value of n1 and n2, these were given in the numerical. So we have used that relation, which is n1 plus n2 plus n3, this is equals to 1. So n3 is equals to 1 minus n1 minus n2. So using this relation we have calculated the value of n3, which is 0.5. Next, to calculate the x and y coordinates of point P, we have used the formula of x, which is n1 x1 plus n2 x2 plus n3 x3. Now here all the values of the n1, n2, n3 and x1, x2, x3, these are known to us. And for this y, all the values like n1 y1 plus n2 y2 plus n3 y3 in this equation, all the values of these parameters like n1 n2 n3 and x1 x2 y3, these are also known to us. So we have put all the values in this equation and we have calculated the coordinates of the point P, which is 2.9, 3.8. So this is the process by which we have calculated this coordinate of the point P, which is inside this triangular element. Let us discuss the next numerical. So here one triangular element is given and its coordinate of its nodes or nodal points are shown in the diagram. Now, for the constant strain triangular element, we need to assemble the strain displacement matrix. Some data are provided here. Take T equals to 20 millimeter and the Young's modulus E equals to 2 into 10 to the power 5 Newton per millimeter square. We need to assemble the strain displacement matrix for the CST element. So let us first write the value of the coordinates which are given here. So the value of x1 is given 100, y1 is 100, x2 is 400, y2 is 100, corresponding to node 2, node J, and corresponding to node K, we are having x3 is 200 and y3 is 400. The thickness is given 20 millimeter and the Young's modulus is given 2 into 10 to the power 5 Newton per millimeter square. And we need to find the strain displacement matrix, that is the matrix B here. So for that, for the CST element, we need to actually calculate the formula for the strain displacement matrix. So this is the formula for the strain displacement matrix that we have discussed in the earlier lecture. And for the strain displacement matrix B, the formula is 1 by 2 A multiplied by this 5 by 3 matrix. Now here we can see within this 5 by 3 matrix there is Q1, Q2, Q3, all these things are written in R1, R2, R3. So what are these actually? Q1 is Y2 minus Y3. So as the values of Y2 and Y3 we can see in the earlier slide, Y2 is 100 and Y3 is 400. So that means Q1 is 100 minus 400, which is equals to minus 300. Next, Q2 is given Y3 minus Y1. This is the formula for Q2. So the value of Y3 is actually 400 and the value of Y1 is 100, which is given in the question. So the value of Q2 we are getting as 300. Next, the value of Q3, it is Y1 minus Y2. So the value of Q3, this is Y1 minus Y2 and it is 100 minus 100, so this is 0. So this is the value of Q3. Next we need to find the value of R1, R2 and R3. So the formula for R1, it is actually x3 minus x2. So the coordinate x3, this is actually given here, it is 200, and the coordinate x2, it is actually 400. So that means the value of R1, it is now minus 200. Then the value of R2, this is actually x1 minus x3. So this is 100 minus 200, so this is actually minus 100. Next, the value of R3, this is x2 minus x1. So the value of x2 was given 400 and x1 was given 100. So the value of R3 we are getting here is 300. So this formula we need to remember to solve such numericals. Now if we substitute all these values of Q1, Q2, Q3, R1, R2, R3 in the B matrix, then we will get this equation number 2. Now first we need to calculate the area of the triangular element, and for that we need to use this formula, that is half multiplied by a 3 by 3 matrix. In this 3 by 3 matrix, we are having 1 x1 y1, 1 x2 y2, 1 x3 y3. So this is the 3 by 3 matrix, and the coordinates, this x1 y1 x2 y2 x3 y3, these are the coordinates of the nodal points or the corner points of this triangular elements, which are I, j, k, denoted here. So we can put all these coordinates here, and after putting this, we need to perform the matrix multiplication, and finally we are getting the area of this triangular element. It is 45,000 millimeters squared. Now we need to put this area value of the triangular element in the strain displacement matrix, that is the matrix B formula. Then we are getting this type of equation. So finally we are getting the strain displacement matrix. This is equals to 1 by 900 multiplied by this 5 by 3 matrix. So this is the final value of the strain displacement matrix that we have calculated here. So what we have done here in this numerical, we had to find the strain displacement matrix for this given triangular element, CST element. Now to calculate the strain displacement matrix, this is actually the formula, that is equation number 1. This formula we need to remember. So in this formula we can see the variables are A, capital A, which is the area of the triangular element, then Q1, Q2, Q3, R1, R2, R3. So these are the variables that we need to find first. After that we need to put the values of this variable. We can finally find the value of the matrix. So for that, the formula of the Q1, Q2, Q3, which are here in this slide, you can see that y2 minus y3, then for q2 it is y3 minus y1. So in this similar manner we need to remember the formula for q1, q2, q3. Next we need to write the formula for r1, r2 and r3, which are related to the x coordinates, you can see here. So after that we have entered the values of this q1, q2, q3 and r1, r2 and r3 in the equation number 1, and thus we have got the equation number 2. Next we found the value of the area of the triangular element, and for that we have used this formula, which is half multiplied by a 3 by 3 matrix. So from that we have performed the matrix multiplication, and finally we have calculated the area. Then we have entered the area in the formula of the strain displacement matrix, and finally we have calculated the strain displacement matrix value. Okay, so this is the procedure to solve such numerical based on the CST element. Let us discuss the next numerical. So what it is given here, we need to determine the stiffness matrix for the constant strain triangular element, which is shown in the figure 1. The coordinates are given in units of millimeters. Now we need to assume plane stress conditions. So it is given, take E equals to 210 GPa, nu equals to 0.25 and T equals to 10 millimeter. So let us first write what are the things given here. Corresponding to node 1, we are having x1 equals to 20, y1 equals to 30 millimeter. And corresponding to node 2, we are having x2 equals to 80 millimeter, y2 equals to 30 millimeter. And corresponding to node 3, we are having x3 equals to 50 millimeter and y3 equals to 120 millimeter. Next, the value of Young's modulus is given in this numerical. which is 210 gigapascal. So giga means 10 to the power 9. So you can represent this as 210 into 10 to the power 9 Newton per meter square, which is the representation of Pascal. So that means 210 into 10 cube Newton per millimeter square, which can be also written as 2.1 into 10 to the power 5 Newton per millimeter square. The unit conversion is actually done here from gigapascal to Newton per millimeter square. Since the value of the Poisson's ratio and the thickness, it is also given in this numerical, and we need to assume the plane stress condition. So to find the stiffness matrix K, let us write the formula for the stiffness matrix K, so which is B matrix transpose multiplied by D matrix multiplied by again B matrix into A and A into T. So this is the formula to calculate the element stiffness matrix for the CST element. Now to calculate the area of this triangular element, we need to use this formula, which is half multiplied by the 3 by 3 matrix. In this 3 by 3 matrix, we are having all the coordinates of the nodal points. So we need to put the values of the coordinates of the nodal points, and then after the matrix multiplication, we are getting the value of the area of the element, which is 2700 millimeter square. So next we need to find the strain displacement matrix, that is the matrix B. The formula for the strain displacement matrix, it is 1 by 2A multiplied by a 5 by 3 matrix. So in this 5 by 3 matrix, we are having 6 different parameters in the form of Q and R. Now the value of this Q and R we need to write in terms of the coordinates. So the value of Q1, it is coming as minus 90, and the value of Q2, it is y3 minus y1, that is 90. Then the value of Q3 is 0. The similar manner, the value of R1 is x3 minus x2, which is minus 30. Then the value of R2, it is minus 30, and R3 is 60. So now we need to put this value of the Q and R parameters in equation number 3. After that, we need to put the value of the area also for this CST triangular element, and finally we are getting this equation number 4 as the B matrix, that is the strain displacement matrix. Now this we need to calculate the D matrix also. So this D matrix, it is the stress strain relationship matrix for plane stress problem. In this question, it is given that we need to assume the plane stress concept. So here, this is the formula for the D matrix, and it is seen that for all the parameters in this equation, the values are actually given. So you need to put the values, actually the values of Young's modulus, then the value of Poisson's ratio we need to put here, and then after the matrix operation we are getting the equation number 5, which is the value of the stress strain relationship matrix D. Now we need to multiply this D into B, that is the strain displacement matrix multiplied by the stress strain relationship matrix. So here, to a matrix multiplication we need to perform. So it is a 3 by 3 matrix multiplied by a 3 by 6 matrix. So we can see the steps of the matrix multiplication. It is given here. So after several steps, we are getting this matrix value of d into b. It is equation number 6. Now the b matrix we have found out already. Then transpose b we need to write here. So it will be a 5 by 3 6 by 3 matrix now. Earlier it was a 3 by 6 matrix. Now it will be a 6 by 3 matrix. Now we need to perform this b transpose multiplied by d multiplied by b again. So that means here it will be a multiplication of a 6 by 3 matrix multiplied by a 3 by 6 matrix. So the steps for this matrix multiplication is given here. And finally we are getting this representation. Now this value we need to multiply with the area and the thickness to get the final value of the stiffness matrix. So if we put the value of the area and thickness, then after several steps we are getting this K matrix value as the final value here. So this is the steps by the help of which we have calculated the element stiffness matrix for the CST element. And the stiffness matrix properties, these are also satisfied here because the K matrix, it is coming as a symmetric matrix, and the sum of the elements in any column, it is equal to 0. So these are the things that we have discussed today. So 4 different numericals we have discussed based on the formula that regarding the CST element, and regarding the strain displacement matrix or stress strain relationship matrix, and we have calculated the element stiffness matrix also for the given CST element. Okay, so this is the end for this lecture today.